Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're going to get started. It's my pleasure to welcome Ting Zhang from Stanford. He's a student of Zohar Manas, and he's been working on decision procedures, something we all care about. He's been doing some interesting work he's going to tell us about, and he's here for today and tomorrow, so you'll be seeing him around.
Thank you, Tom. Thank you very much for coming to my talk. The talk is about arithmetic. Okay. Thank you. So, what is a decision procedure? An algorithm that checks whether a formula is satisfiable or not satisfiable. So you can picture a decision procedure as a black box. The input is phi, and the output is whether phi is satisfiable or unsatisfiable. So theoretically, you can say phi is whether phi is valid or not valid. So a key feature for a decision procedure is that it always terminates with either positive or negative answer. So in the program verification, we get thousands of verification conditions, and most of them are mathematically uninteresting but tedious long. So we need this automated theorem prover to relieve users from tedious interaction with the theorem prover. So only by this way we can make the program verification practical task. So why do we need new decision procedures? We have many decision procedures floating around already. So for example, in arithmetic, we have decision procedures for integers, for reals. We have decision procedures for data types such as list, queues, arrays, sets, multiple sets. So, but unfortunately, program languages are very complex entities. So in general, even a very simple programming language contains multiple data domains and so multiple data types. So that results in constraints spanning over multiple theories. So usually we don't have verification condition for in one single theory. So we need the ability to reason about mixed constraints from multiple data domain. So what's our common mixed constraints? In this talk, we consider two types of constraints. Actually, one type, we talk about data structures with integer arithmetic. So first, we study the term algebras, which model tree-like data structures with integer arithmetic. Then Q, which model linear objects with integer arithmetic. So we can use the theories to analyze data structures and their quantitative properties. For example, we can reason whether there's a memory heap buffer overflows, whether there are out-of-bound array of size. Also, these integer properties can allow us to reason on augmented data structures. We will see in the example soon. So here is the tree rotation examples. See, the left code, there are 4 lines in the left code. And what it does is to do a left rotation on the tree. So we keep alpha, beta, gamma in order, but somehow we switch the order of C and A. So question is whether this operation will memory safe. The size of X is still equal to the size of Y. So from the picture, it's quite clear, right? The tree structure doesn't change much with respect to the size. But it's not clear from the code at the left-hand side. So we will see our decision procedure will be able to answer these questions. So string operations. So The left code, function A, is not safe because there's no boundary check. There could be a buffer overflow risk. And the function B is safe because we have this, we use string ncopy. Actually, we won't go beyond the space we have declared. So which string manipulation is memory safe? And this is a big question. And this kind of code happens in a lot of places in C language. So we will say the decision procedures for queues with integers will be able to automatically discharge every conditions related to this issue. So there's another string operations. Codes of this kind often appear in the C codes. So it basically, for the correctness of this code, we require that the P ends with the noun. Because in the while loop, this is a termination condition in the while condition. And if this code does not terminate, there could result some memory disasters, segmentation fault, because this code can overwrite or change the memory segment, which it should not be changed. So we need to reason whether this code segment terminates, whether there's a memory safe. This is another example on red-black trees. We can use integers to express additional properties on trees. So a tree is a red-black if only if they satisfy the following 5 conditions. The last 2, 4, and 5 are crucial. So basically 4 says every right node should have 2 black children. 5 said all paths from the root to the leaf should contain the same number of black nodes. So how about reasoning on this balanced tree structures? We will say our decision procedure will allow us to do this job. So how is the combining decision procedures? So since we're talking about the constraints from data domains and the constraints from integer domains, it's natural to ask these questions. So when people talk about combining decision procedures, they usually have pictures of this kind. So a decision procedure P1 for T1 and P2 for T2, and we are looking for a decision procedure P for T1 union T2. So the combination work all started by Nelson Open in 1997. This framework called the Nelson Open combination. And it requires that the theory to be combined to be quantifier free, and they do not share a signature, function symbols, or practical symbols. So recently there are some advances to relax these constraints, these conditions on the combination. So people try to extend this work to non-disjoint signature, and there are model theoretical work to find out the model theoretical conditions when this combination is possible. Also some proof theoretical work. So, but all existing techniques put severe conditions on the combination, on the theory to be combined. And specifically, none of the techniques is applicable to multiple sorted theory with functions connecting to different domains, as in our case. Here's our slogan: logical theory are fragile, and the Nelson open combination should be viewed as exceptional. So when they are useful, but we shouldn't expect the modularity in the more generic cases. So instead, we should concentrate on concrete problems instead of looking for grand scheme. So here's our approach. We try to exploit the algebraic properties of the component theories. So for quantifier-free combinations, we extract exact integer constraints from data structures. For quantifier combinations, we try to reduce the quantifiers on data structures to quantifiers on integers. So in one slogan, we reduce theories of data domains to theories on the integer domains, on the integer domain. And so eventually, we are going to deal with the decision procedure with integer arithmetic. So here's our contribution. We have decision procedures for data structures with integer arithmetic. This is essential for practical program verification. In specific, it can express program memory safety property, and also can express augmented data structures. So the main approach is to exploit the algebraic properties of component theories. Here's the main challenge. The integer constraints we are going to extract must be processed. In other words, they are actually satisfiable with the data constraints. So the second contribution, we use the techniques developed for the term algebras with integers to prove the decidability of the first-order theory of Knuth-Bendix Order. This was a long-standing open problem in term rewriting community, and it was officially listed as the RTA problem 99 in 2000. So this is an important result. Yes?
Does that mean that there are problems 1 to 98 also?
I'm sorry?
So what does that number 99 mean?
They have a long list of open problems.
There are problems 1 to 98 also.
Yeah, now it's more than 100. And some, maybe a third of them has been solved. Okay. So before that, before our work, there are many partial solutions. For example, they have solutions for quantifier-free theories and for unary quantifier theories, in which that we only have the unary function symbols. And it's also interesting to see that the same approach is applicable to a very different problem. So here's my talk outline. So I talk about term algebras with integers, then Knuth-Bendix order, then Q with integers, and at last, the conclusion, ongoing, and the future work. So this is the part 1. So some previous work on term algebras for quantifier-free theories, this work was done by Nelson, Open, Donny, Thessey, Tarzan. And the decidability of the quantifier theory was proved by Malsiv using quantifier elimination in 1971. And recently there are some extensions, not very recently. So people study infinite rational trees with memberships, featured trees. Basically, we can have the dynamic arities in the tree structure. The theory of term powers, which is the extension of term algebra with the predicate. So here's the term algebra we are going to study in our talk. It has 5 components. T denotes the term domain. C is the domain of constants, constructors. A is the domain of constants. We require A is a subset of C. And A is non-empty. So S is a set of selectors. So for each constructors with arity K, we have corresponding K selectors or projectors to get the case subtree. So we have testers. So is the alpha of T is true if only if the outermost function symbol of T is alpha. So there are 2 essential properties for term algebras. The term domain T is generated exclusively using C, and every element in this domain is uniquely generated. So here is an example of term algebra. So the LISP is an instance of a term algebra. So we have 2 constructors, cons, neo. We have 2 selectors, car, coulter, and neo is the only constant. We have corresponding 2 testers, is neo, is cons. So the following sentences, actually the sentence schemes, axiomatized the theory of LISP. For example, the last sentence says that if X is a proper tree, then we first do the projection, then do the pairing, we get back to X.
Can you go back 1 second?
Yes.
So I was thinking of cons and car and cutter all as constructors. Is that not the case?
Car and coulter are selectors.
Car and cutter are selectors.
Yeah. Con is the only constructors in here. Actually, nil is also a construct, but it's a constant.
Okay. You're asking to say that is nil of nil false, but
so the first axiom says x is nil if only if it's not count is disjoint. So, so could you repeat?
It's implied by the axioms.
I see. The two predicates are. I see. So the subscript means is meaningful. That is, it's not just two names in the last two. The is nil and is cons are somehow tied to the function, to the constructor's cons and nil.
Yes. Okay. Yes.
If you heard it that way, right?
So here is the theory we are considering in the combination. We have Pressburg arithmetic denoted by LZ and PA. The term algebra, the language is LT, the structure is TA. We are studying a two-sorted language. Basically, these are theoretical, set theoretical combination of two plus the one function, which we call the length function, which will return the number of symbols in a term. So we choose function as it is for simplicity. In general, we can choose weight function. Then we can assign each symbols a non-negative integer, or we can just choose the length function to be the height of the tree. And this requires no essential change to our techniques. So here is the problem. So the presence of integer constraints restricts solutions to term constraints. For example, in this formula, it says x not equal to A, x not equal to B. Actually, A and B are only two possibilities of trees of length 5. So if x not equal to either of them, then x cannot have the length 5. So this one will contradict the constraint that x has length 5. So there are hidden constraints on data. Yes?
So you're assuming that you cannot have cyclic.
It's a term number.
No, we don't have the cyclic stuff. Yeah.
Just to test my understanding, the size of cons, nil is 3 or 5? It's 3, right?
5. We also 5. Yeah, we count every symbols in the term. So
go back one slide, please.
There should be plus 1. Yes. Thanks.
That's fine.
There's a plus 1 missing here. Yeah.
So you're saying that, okay, so you know that x is not either of these two data structures, which each is 5.
Yes.
Size 5, but there are other data structures of size 5.
That's the only possibility. That's the only two possibilities.
Those are the only two, of course.
Yeah.
Of course. Right.
Yeah.
Okay.
So you see there are hidden constraints on data structure length that contradict the integer constraints. So we are going to find this thing out, which we call the length constraint completion, LCC. So we see the phi delta is an LCC for phi t and phi z. Phi t and phi z denotes the combined constraints. If only the following two formulas are satisfied. So we will explain these two formulas in the later slides. So here, informally, the phi delta fully characterize the combined constraints. So they are the phi delta is equally satisfiable with phi t and phi z. By doing this, we reduce combined constraint to the integer domain.
So t is your term. I'm sorry. Go ahead.
I will explain.
Okay, so t is your. I'm sorry. Then can I ask the question?
Yes.
So phi sub t is your term, is your constraint on the terms.
Yes.
And then phi sub z
is integer constraints.
But restricted somehow to just lengths of the terms, sizes of the terms.
it can be any integer constraints, but it may contain the length term. Say the length of x is greater than length of y.
Oh, I see. So right. So okay.
So,
okay.
And length only is applied to variables. Is that?
It can apply to any terms.
Oh, so you could select. You could do length of car of x.
Yeah, length of car of x, comma y. Yes, length of car of x. Yes, you can do that.
So 5C is not pure.
Yeah, in this sense, you can see it's not pure. Yes.
And then delta is.
Delta is not pure either. So delta has the same form as phi z. But here we see that phi delta is a fully calculation of the combined one. Maybe we'll see an example in a few slides later.
But I think the question is but based on what you said, it sounds like you've completely eliminated all mentions of terms. Everything's integer, I thought, in delta.
Yes, but only after certain normalizations, we can assure that certain inconsistency, the term has been consistent. The constraints on terms is consistent. Then we can do the reduction. So obviously, we don't allow the contradictory terms in the literals in the term constraints.
I guess the question was really more about the syntactic form of psi of delta.
Yeah,
what symbols can be in it.
so one example is coming in 2 slides. Yes.
So let's say you don't have any integers in your formula, then the reduction that you do, is that reduction the same as the other algorithms that reason about algebras?
Yes. Suppose there's no integers, then we don't need to do this reduction. We can just use any decision procedures for term algebras.
What I'm asking is that how do those decision procedures compare with your algorithm for checking satisfiability in case there are no integers?
So our decision procedure based on, for example, the Nielsen-Opens decision procedure for term algebras.
So can you also give me a bit background about what is the complexity of reasoning about only term algebra formula?
So for term algebras without the selectors, then this is just linear on time, because you only have constructors. But with selectors, the things goes complicated. It goes to NP complete, because a selector. So for each select term, you're not sure whether it's a proper select term in the sense whether, suppose we require that if x is an atom, so car of x should be equal to x. But you don't know properly whether x is an atom or not. This will, to eliminate this ambiguity, this involves the exponential blow up. So this, with the selectors, this became NP complete.
I have another question about term algebras.
Yes.
Can you actually prove that x equals cons of x comma y, that is a given structure is cyclic? Can we actually prove that is unsatisfiable from the list of axioms entry? Suppose I say x equals cons of x comma y, that is satisfiable only.
This is unsatisfiable in our theory. Yes.
And you can prove that from the axioms.
Yes.
So when should we use then this theory to model, like what construction programming languages, car, cutter, and cons as a term algebra, if you view it as a term algebra? When is this useful then, since you cannot model cyclic lists? So maybe when you're modeling when you're only talking about acyclic data structures,
Functional.
Yeah.
I think perhaps we should let him go on.
So all tree structures has no loops, right? So you can use the term algebra to model all tree structures. For example, red-black trees, you don't have the loops, right? Yeah.
Well,
Okay. So let's analyze the issue conditions. So the first condition, let's call the phi delta plus to be the formula when in place of phi delta satisfy the first condition. So phi delta plus actually says that the length constraint, the length function maps a satisfying data assignment to a satisfying integer assignment. You can see that if the left-hand side is satisfiable, then there exists an integer. So basically that means that the length function maps a satisfying assignment in term domain to satisfying assignment in integer domain. And the reverse side we call the phi determiners to be which is the formula satisfying the second condition when in place of phi delta. So phi determiners states that any satisfying integer assignment is an image under this length function of a satisfying assignment, of a satisfying data assignment. So basically that means any satisfying integer assignment can be realized as the length of terms. So say the left-hand side there is a satisfying assignment, then there exists a term such that the right-hand side hold. So the bar, by using the bar, we denote a sequence of variables. Yeah. So if we identify constraints with the corresponding solution size, we have the following relation. So phi delta plus is an over approximation of phi delta. So phi determiners is under approximation of phi delta. So put all this together, we can say that phi delta must be unique up to equivalence. So here's an example.
What was the prime there?
Yeah, suppose there's another phi delta. Phi delta prime is another constraint satisfying the two conditions, right? So the phi delta prime must be also a phi delta plus and a phi delta minus, so it will sandwich the phi delta in the between. So we see this uniqueness up to equivalence. And so here is the syntactical form of the phi t and phi z. So phi t says, okay, x not equal to the smallest binary tree, or neither does y, and x not equal to y. So phi z says the length of x must equal to length of y. Then we see that this constraint, the first one, phi delta plus, is sound, because every node must have the length of every tree must be an odd number. So we require 2 does not divide the length of x. So, but it's not realizable because it makes not every solution to phi delta plus is realizable as phi t. Specifically, we can choose the length x to be 3. Then it's not realizable because obviously it's not realizable because there's only one tree of size 3 and x, y are not equal to this tree and x not equal to y. So if we strengthen this constraint, over strengthen this constraint phi delta plus, then we get the phi delta minus, which says, okay, we require the length of x greater than 5. Certainly every satisfying integer constraint can be realized, but it will miss 1. Basically, the length of x is equal to 5, right? So in the end, we have this phi delta, which is sound and realizable. We call it an LCC for phi t and phi z.
I'm sorry, where did 5 come from? Just pull that out of the hat?
Oh, you mean phi t?
Where did 5 come from, the constant 5? You just invented that?
This is just an example. If we require this to be greater than 5, then we will miss a solution, which
the 5 was somehow derived from the phi sub t. How was 5 derived?
Well, we do not derive this 5 from this. See, there are enough number of trees to satisfy the phi t. Suppose the length of x and the length of y are both 5. There are how many trees? At least 2 trees, right? 2 trees, right? So we can assign x to be. Let me go back to the example. We'll see.
You just want to prove existence, so it doesn't matter where the 5 comes from.
Okay.
The question is, okay. So you just.
Oh, oops. Sorry. So So here is our main theorem that let L.
Can you go back one? So the last one, pi sub delta, what is that? That's a combination of the two constraints. It's just a conjunction.
No, they have no relation between them. This is not a conjunction. So what I'm saying is just an example that this is the phi delta we are looking for.
Okay, that's the one you're looking for. And delta plus is an over approximation?
Yeah, and phi delta minus is under approximation. Yes. So here's our main theorem that given the combined constraints phi t and phi z, and we can compute the phi delta to be an LCC for phi t and phi z, then whether the phi t and phi z is satisfiable in the combined domain, we use this to denote the satisfiability. If the phi t is satisfiable as the term in the term algebra, and the phi delta is satisfiable in the prescribed arithmetic. So in this way, we can utilize the previous design decision procedures for this combined domain.
What does LCC stand for?
Length constraints the completion. We just the formula phi delta which satisfy the two conditions. Mm-hmm. Yes.
The way you reduce those constraints. So how did you get the constraint that 2 does not divide the length of x?
So we didn't derive in specific, but this is just an observation that any tree, according to our length function, must have odd number as the length. So here is our generic decision procedures.
So I don't understand this. So supposing I come up with my own length function.
Yes.
Then what happens?
Then you need to
do the all work that you did again for that length function.
Not all the work, because the framework is here, and you probably need to change some things. Yes.
Okay.
Yes. Say for weight functions and for the height functions, we see basically there are little change for this our techniques. So here is the generic decision procedure. First, we test whether phi t is satisfiable in the term algebra. Suppose it fails, then we fail. Otherwise, the decision procedure will actually the computation is like the building a decision tree. We use the superscript I to denote each branch. Sorry. Wow. Yeah. So suppose then for each branch we compute the LCC, and then we say we only return success if there is a successful branch. Otherwise, we return fail. So now the decision problem reduced to the computation for LCC.
What is a partition? Can you explain what a partition is?
So basically, suppose we have A not equal to B or A equal to B, then we do the disjunctive splitting. Then we get two branches. And you can see this as a partition of the search space. Okay, thanks for the question. So now let's go back to look at the tree rotation algorithm. So we do the post-condition computation. So the phi 0 is the initial condition before the first statement. And phi 4 is the post condition after the run of the statement 4. Then our decision procedure will be able to prove that phi 4 implies the length of x is equal to length of y. So we also show how to use our technique to model the red-black tree. And so we consider the theory of this kind. We have the term algebra TRB, red, black, nil, and three constructors. Red denote the red node, black denote the black node. The max denote the we have two integer functions instead of one. So the max denotes the maximum number of black nodes on a path, and the min denotes the minimum number of black nodes on a path. Let's look at the definition. So the max is defined as follow. First, if x is a nil, because every nil will be treated as black. So we have 1. Then we have 3 cases for 0. Basically, when we return 0, we mean that the red-black tree property has been violated. There are 3 cases. Suppose the root is red, but the violation has happened in the subtree, so we return 0. Suppose the root is black. So suppose this covers the first the condition, the item 2 and 3, and the fourth says suppose the node is red, but it does not have 2 black children. Then this is also a violation, so we return 0. Otherwise, suppose the root is black, then the path is the maximum of the children plus 1. If it's red, then we don't do the plus 1. So similarly, we can define the length function for min. After this, we can express whether a tree is a red-black tree. So if the first condition says the length of x, the max, is equal to min, then that means any path contains the same number of black nodes. And the max is greater than 0. That means any red node must have 2 black children. There's no violation in the subtree. And the root is black, denoted by is black of x. So the choice of signatures, the length functions will trivially satisfy other conditions. Say the nil node is black, every node is either black or red. Yes?
So I'm a little confused. In your original statement of the problem, I understood you to say that there is only one function on these tree structures, which is the size.
Yes, yes.
So it turns out that that's not the case, because you can define your own functions depending on your application. For example, here you define the max function and the min function.
Yes.
And your algorithm will work no matter what function I write?
No. I mean, there's that's what we call it the generic decision procedures. So the decision procedure will follow the same structure, but certainly you need to tune up with different length functions. You need to tune up specifically for the 2 function cases. And if you have 3 functions, you may need to make another change.
I see.
So, as we said, the decision problem reduced to the computation of LCC. So, it depends on how you compute this LCC according to these functions. Certainly, the computation is different. You're certainly right. We need to make a change, but not big change.
But you have to specify the axioms about these max and min functions computation.
Because we didn't, we don't need to axiomatize these functions. We just show how the function is defined. Because we use decision procedures, we not a general theorem prover, so we do need to build in these axioms for them.
Do you use generic algorithm for computing LCC also, or is that something that I have to do every time with these new functions and I have to prove its correctness and so on?
There's no generic way to, once for all to solve this problem. For the size function, there's a way. For weight function, there's another way. But there's no big change between them. So once you know how to do this with length, then you can easily derive how to do with the weight. And so for the height. And yes, it doesn't cover, it's only cover 3 functions so far, but yes, it doesn't cover many other functions, but it really depends on the properties of these integer functions. As far as I can see, the reasonable definition has been covered.
So it's not true that any primitive recursive length function
No.
LCC.
No. Because another thing is this can only deal with things can be defined in principal arithmetic. This is the upper limit. Not every recursive function can be. So we also have result for quantifier elimination. So just recall that to do a quantifier elimination is the surface to eliminate existential quantifiers from primitive formulas of this form. For example, this form has begin with a block with existential quantifiers and a conjunction of literals. So we also assume that each literal is not of the form x equal to t, if x doesn't belong to t, because we can do a simple substitution to get rid of this existential quantifier. So the result goes like this. We can remove a block of quantifiers in one step, regardless how long the block of quantifiers is, as long as they are of the same type. And this almost optimal complexity for each alternations, we only introduce one exponential blob. Remember, the term algebra itself is non-elementary, so this is unavoidable in the worst case. So here's the related publications. We have decision procedures for recursive data structures with integer constraints. This is the original paper published in each car 2004 and won the best paper award. So we have this quantifier elimination in this paper in the TB Hall 2004, and the combined journal version is going to appear in the information and computation. Yes.
So in typical red-black trees, you do destructive update of the references. You don't handle that, right? You're assuming that you do entire tree copying in an implementation, right?
Yes. Thanks. So this concludes the first part. In the second part, I will talk about the decidability of Knuth-Bendix order. So the ordering is very important. Am I overrun with time? Okay. So we have the ordering is very important in the computer science. It happens everywhere. Example, in the termination proof, we need to rank the program states. So in order the resolution, we're considering, we only do the resolution between the terms which are maximum with respect certain ordering. So in order the rewriting, we can orient the equations, commutative equations, dynamically according to the ordering. So the central problem for all these applications is to decide the satisfiability of order constraints. So in most cases, the decidability for quantifier-free fragments is enough. But the case arises when we need more powerful decision procedures to reason on quantified fragments. In this example, this is a simplification rule in ordered rewritings. So C and C prime denote the ordering constraints. And this rule says the S to T can be simplified by U to V at the position P in S. So providing that for all variables in S, there exists a variable in U such that this ordering constraint is satisfied. So why? Because if this is satisfied, then we can reduce, we can remove S to T, because whenever X to T is applicable, we can use U to V instead.
Can you go back? I just want to pass this slide. So the problem that's defined is you want to check whether some set of constraints implies an equality.
Uh-huh.
Yes, what is the problem?
So C, yes, C implies C prime and the the position P in S is equal to U. So this one is a literal 2, right? So this is a constraint. I mean, by S P we denote the position P in S, and I mean this is.
So U to B is a substitution that you're going to apply to,
yes.
to S, and you know that S rewrites to T, or S reduces to T?
Suppose we want to use S reduced to T, right? Because then in this case we can use U to V because the position, when we substitute U in the position P, we get T. So instead, using S to T, we can use U to V instead. But to be able to do so, we need to make sure this constraint is set.
So this is like a strengthening. You're saying instead of, you have an equality. Under the substitution U to V, S to T becomes an equality.
Not exactly. Yeah, you can say as equality. Yes, yes.
I don't even understand how to parse even just one formula above the line. So you have S arrow T bar C. What does that mean?
That means we only do this rewriting under the condition C.
So is C a Boolean condition?
Not Boolean condition.
What is condition? What does condition mean?
This could be an ordering condition. Say, for example, it requires that the order of X is greater or at least equal to order of T.
So these are the Knuth-Bendix constraints.
It could be Knuth-Bendix order constraints or any other order constraints.
And this is a conditional rewrite?
Yeah, conditional rewriting, yes.
Okay, so S arrow T given C is a conditional rewrite rule.
Yes, yes.
Comparatively, the arrow, which is much wider, has stronger binding power than the vertical bar.
Absolutely.
Is that right?
Right, yeah.
Yeah, you can see that, yes.
Okay, so you have a conditional rewrite system, and you want to check whether something rewrites given that conditional rewrite system, and then your result is that yes, you can check that.
Yes, yes.
Mm-hmm. So then you have two conditional rewrites above the line. Then you have one conditional rewrite below the line to the left, and some equality on the right.
Oh no.
It turns out that the one on the left is the same as one on the left below the line is the same as the one on the right above the line. So why is that?
I use the matrix, so actually I need to shift the things to the right. Actually, yes. So the S to T has been. You can see this in this way. If we have two conditional rewriting rules, then S to T we can eliminate it because this is redundant in this.
The U to B rewrite still might be applicable, but the S to T is no longer needed. It's replaced by the equality.
Mm-hmm.
If you've been coming to Andrei Vorontov's lectures, you would have been learning a lot about some of the issues here. The fact that I'm even able to slightly parse this is only a result of attending some of Andrei's lectures. But I'm sorry, that's a technical comment. But now okay. So we still have some understanding of. So there's the long bar there, and what is this if line saying now? You're saying that.
What about there's one more formula before it that has two things that I also don't understand. S square bracket V means substitute V inside S.
Yes. At position P. Yes, at the position. Yeah.
And what does the vertical bar later sub P? That's not the same vertical bar as we see in other places.
Yeah.
You mean this one?
Yeah. What does this mean?
This means P is a kind of position path, and S bar P means. I'm sorry for the confusion. Yes, there are too many bars here. So this means the terms in position P. For example, allow me to use this. There's no pen. So, here. There's been no solution. Then suppose this term is t, and we call this position 1, this position 2, and this position 1, 1. So t 1, 1 is equal to c, t 1 is equal to t 1 is equal to cons cb, t 1, 1 is equal to c. I think it's clear now.
So you could use P. P is a sequence of selectors, really. Is one way to think of it.
Yeah. You can view as a sequence of integers to identify the position. Yes. Okay.
Let's go on.
Okay. Fine. So there are mainly two types of orderings in this term rewriting literature. So one is called LPO, lexicographical path ordering. So it of purely syntactical nature. It has two components, syntactical precedency and the lexicographical extension on itself. So there also another ordering is called Knuth-Bendix ordering, which is of hybrid nature. It has three components in the definition. Besides the two, they have the numerical ordering. We will see the definition soon. So, as I had before, for the decidability status for quantifier-free theories and unary quantifier theories, we have positive results. But for the general quantifier theories, we don't know. We actually know that the LPO is undecidable. And we answered this question positively, that the general theory of KBO is also decidable. So that's the good news for solving the ordering constraints of the aforementioned type. So here is the definition of Knuth-Bendix order. A Knuth-Bendix order is defined with two parameters. One is the weight function. Now we have weight function. See, we can assign each individual symbols a non-negative integer. And the weight of a term is the sum of weights of all its subterms, of weight of all symbols in it. Also, the second integrand in this definition is a linear precedency order on the constants, on the constructors in the domain. So the definition has three clauses. First, we compare the weight. This is the numerical part. So the u is less than v, we denote by less super kb v, if only if the weight of u is less than weight of v. Suppose the weight is equal, then we compare the type. The type of u denotes the aftermost function symbol of u. So we compare whether the type of u is less than type of v. Suppose this also equal. That means that the two terms are totally similar on the top. Then the KBO is defined by its lexicographical extension recursively. So it says that u is less than v if only if there are children ui, which is less than the corresponding children vi, and all corresponding children are pairwise equal before I. So here is the main idea we call the depth reduction. The depth of X in a formula phi is the length of the longest selector sequence in front of X in phi. So suppose there's no selected terms in front of X, we say that the X has depth 0 in phi. And we see the formula of this form is solved in X. When this happens, the elimination became easy. We will see soon that suppose phi is solved in X, then we can assume that the formula has this form, that it has three parts. The first part said that the UI X has a bunch of lower bounds called UI and a bunch of upper bounds. And something has nothing to do with X. We call it denoted by phi prime Y. So the elimination goes like this. We only need to make sure that there is enough space between lower bound and upper bound. So we use less sub 2 in generalize sub n to denote a new order called the gap order, which states there are increasing chain from x to y of length at least n. So the elimination is, so there exists x, phi eliminate to this one, which says that every lower bound, there is an element, there is a room between every lower bound and every upper bound. So we can fit x in. That's the elimination, the whole idea of the elimination. So here is the high-level structure of this elimination. The where loop, the outside where loop says as long as we have job to do, we need to do it. And we have two conditions. Suppose there is a x such that the depth of x in phi is 0, then we do elimination. Otherwise, we must have the negation of the conditions. Then we do depth reduction to create the conditions to do elimination. So this is kind of greedy algorithm. We try to do elimination as soon as possible. So this work has been was published in the last year CADE, and a journal version is also in preparation. So that's the end of the part 2. In part 3, we have studied the decision procedures for queues with integers. So some previous work, the quantifier free theory with the subsequence relations, was done by Bjørner in 1998. And for quantified theories, quantifier elimination procedure was given by Rubin and Voronkoff. They are only dealing with the theories without subsequence relations. So people also extend the work with prefix relations. Also, it has some relation with WS1S. So here's the fundamental difference between term algebras and queues. So term algebra term is constructed uniquely. For example, because we are talking about trees, and the tree structure must be unique. And say if we have ABA, but a queue with ABA can be constructed in many ways. So we can either add A first or add B first, and so on. So this is a fundamental difference between two structures, and they require a new treatment to the normalization procedure. So let's look at the structure of queues. We have C as the constructors. We have left insertion and right insertion. To left insertion add elements in front of queue, and the right insertion add an element at the end of a queue. So we don't have selectors for simplicity, but the language is as expressive as the one with selectors. So here is the decision procedures for queues due to Bjørner, and assume the input constraints has two parts. E is a set of equalities, D is a set of disequalities, actually a conjunction of equalities and a conjunction of disequalities. First, we normalize phi to phi prime. So we get E prime union D prime. And this normalization will find out the inconsistency. If not, then we return success. So this is a high-level structure of the decision procedure. Similarly, we have this theory queues with integers. We can talk about the Pressburg arithmetic. This is the theoretical union of two of the Pressburg arithmetic and the theory of queues plus the length function, which returns the length of a queue. So here is the problem. In the term algebra, we can partition terms in stratified clusters and construct a satisfying assignment inductively. So basically, we only need to make sure that this equality are respected. So the complex term on the higher cluster, the disequality between complex term on the higher cluster has been implied by the disequality of terms in the lower cluster. But here is not the case for queues. So suppose the x not equal to y should be in a lower cluster, But see, there are infinitely many assignments of this form, which will satisfy x not equal to y. But neither ax not equal to yb, nor xa not equal to by. Here I omit the concatenation operator, just put two things together. So the solution, we need to find a cut length. So what is the cut length? The intuition is simple, that a constraint on Q itself, without integers, it can be satisfied by sufficiently long Qs. So there must exist a cut length delta such that any integer solution beyond that can be realized by Q variables. But unfortunately, delta is not the smallest integer solution for such that there exists a term solution. For example, suppose let's consider this constraint. If we require the length of y and q to be 0, we have a solution. Basically, we can just x and y to be empty q. But there's no solution if we require the length of x and y to be 1. This can be easily checked by enumerating all possibilities. So how to do the computation? We need a little bit terminology. We call the orbit alpha to be the size of words of this form. Basically, we just repeat alpha and any words in this infinite sequence is called in the orbit of alpha. And we say a strongly primitive word, beta. Beta is strongly primitive if beta is not in the track, in the orbit for any alpha. But here we require the alpha plus. That means in this set, alpha at least repeat once. So the prefix sub phi denote the set for all words alpha, such that either alpha x or alpha is a proper term in phi q, and the d sub phi, the shortest strongly primitive word d, such that d does not belong to orbit of alpha for any alpha in the prefix set. So the intuition is that the d phi is the delimiter, which we want to make sure that the delimiter does not overlap with itself. So that's all this terminology is about. So we let the LD to denote the length of d phi. Also, when we have the right alignment, we also want to make sure x not equal to y. How to do that? We introduce LC to be the smallest number of letters to create a unique identifying word called color for each Q variable in the constraint. So put all these things together, we call LT to be the sum of LC plus LD, and then we claim this LT will be bigger than delta. So that's the ABC of cut length. Let's look at an example. So let's consider this constraint again. We say that the prefix set to be AB, BA, and AA. We choose LD to be 3. In specific, the delimiter d phi to be AAB, which is strongly primitive and not in any track of the prefix set. So LC to be 1 because there are only 2 Q variables and 1 bit is enough to distinguish them. And so we put together, then we have LT to be the sum, which is 4. So after that, we can apply the LCC computations as before to get the decision procedure. So for richer series of Qs, we have decision procedures for Qs with prefix relations and the integers, which considerably new normalization is required. Also, we have the new normalization to deal with parameters, so we can do the quantifier elimination for Qs without prefix, but with integers. So here's the examples. So I say whether this string operation is safe or not. Here is the string copy operations, which can be the precise semantics can be characterized in the theory of queues with integers. The second example, we want to make sure that the P ends with 0. So then we do an inductive proof that such thing, the row 2 and the row 3 denote the transition relations of the statement 2 and 3 respectively. So this can be proved in our decision procedure by our decision procedures. So the publication, this paper was published in the last year FSTTCS 2005, and a journal version is also in preparation. So here's the conclusion. In summary, we have showed the decision procedures for combining data structures with integer constraints. They are able to model memory safety properties in specific, and they are essential for practical program verification. We show the decidability of first-order theory of Knuth-Bendix Order, and solve an open problem, RTA problem 99, and itself is an important result for term rewriting. So our slogan is to exploit algebraic structures, properties of concrete domains. So we are doing implementation and experimentation. So now we are implementing the decision procedures for term algebras with integers. We also trying to model more data structures, in specific augmented data structures, such like order statistic tree, AVL tree, interval tree, and so on. So third, we try to extend the combination to with other combination frameworks. For example, we want to see whether we can put term algebra queues with length functions together. So another thing to consider is the efficient quantifier-free fragments. Our vision is the forward propagation will keep signs. So positive fragments could be enough. Also, in the end, we're looking for solve constraints of the specific form. We call it entailment constraints, whether the post condition will imply goals, which certainly it has two benefits. Either it can for this kind of framing, we can have more expressive power, introduce more predicates, and also, on the other hand, it could be implemented more efficiently. So, also related to the more expressive language, we can consider the term algebras with the subterm relation. So we see this kind of approximate pointer structures in some sense, and when this apply to Q, we get the Qs with subsequence relations. Namely, we have prefix, suffix, and sub-Q. With all these three relations, we can model most string operations in C. In specific string copy, string incopy, compare, string cat, and so on. So on the theoretical frontier, we already have the Q plus integer plus prefix and sub-Q. The next step should be Q with integer with all these three subsequence relations. This theory is very expressive and have many consequences. Suppose it is decidable, it can interpret the theory of concatenation with integers. So the decidability of this one will imply the decidability of this theory of concatenation with integers. So it can interpret the theory of arrays, and it has hope it can further augmented to a theory of unbounded bit vectors, which will be useful in hardware verification. So that concludes my talk. Thank you very much.
So you mentioned across all throughout the talk that you can, with these decision procedures, prove various things like some properties of red-black trees and so forth. What have you built these decision procedures into? A theorem prover, program verifier?
We build a standalone decision procedures using Java.
So each one of the ones that you mentioned, I mean, you built a standalone decision procedure for that, and then how do you generate input for it? That is, how do you generate verification conditions for a particular program, or more precise? When you say that your decision procedure can prove a property about the red black tree, I can't remember what it was actually. What property was it about?
Oh, I didn't list the specific properties. Basically, all these transaction relations can be expressed in the theory. So then we'll be able to verify the programs.
Have you actually done that?
We haven't done in the programs yet.
Okay. Right.
Yeah.
So you have a theoretical result that says that you can handle all formulas of a certain kind, and you imagine that the formulas that would come up when proving something about red-black trees have that shape, and therefore you would be able to handle it. Am I understanding that correctly?
Yes.
So far, you meant on the last slide you had the theory of concatenation with integer constraints.
Oh, yes.
Is that
A quantifier free fragments.
so? Isn't that open?
Yes, that's open problem.
Whereas
So-
the second bullet is
This is done.
interpret arrays because it just falls into your class. Now, arrays